Hello everyone. I'm going to discuss the proof, the justification for one of our sum or difference identities. Specifically, I want to take a look at the difference of angles for cosine. So we're subtracting two angles. So starting off here with our unit circle, the first thing I need is two arbitrary angles. So I'm going to put a couple points on the unit circle. So let's say we have a point over here, and then I will connect that to the origin, and this will be the terminal side for one of our angles. So let's say starting at the positive x-axis and then rotating all the way over to this terminal side. Let's call this, we'll call this one alpha. So we'll use the Greek letter alpha for that. And then I need a second angle. So then let's put another point. We'll put this one over here. Again, that's going to be the terminal side. So let me connect this together. And then this angle, starting again from the positive x-axis, and then ending up here, that angle, let's call this one beta. Okay, so those are the two angles that we're going to be working with. And both of these angles, we have the terminal side, and the other side of the angle is that positive x-axis there. So we got the angle starting at the positive x-axis, rotating all the way over to this terminal side, and then our second one starting at the positive x-axis, rotating up here. Now the angle that I'm really interested in is the difference between these two angles. So if I take angle alpha and I subtract away angle beta, so starting from this terminal side, if I just rotate back however big beta is, that angle would represent alpha minus beta. So I'm just going to kind of eyeball this here. Both these angles are completely arbitrary. So okay, that's about that big. So then rotating back, so maybe that point there. And then this would be the terminal side of alpha minus beta. So then going from our positive x-axis and now rotating to here, this is alpha minus beta. Okay, and that is the angle we're interested in. We want to figure out what the value of the cosine is for that angle. All right, to do that, I'm going to need to name these points. This one is easy. This one is the point 1, 0. And then I'm just going to go around. Let's name this one A. And let's say this is B. And I'm just going to use some arbitrary values for x and y here. So x1, y1. Let's say this is C. And then we'll call this x2, y2. And then lastly, point D down here, x3, y3. Great. Okay, so the next thing we're going to take a look at is some of the sizes of these angles here. Like I said, the one we want to take a look at is this alpha minus beta. But if we take a look at some of our other angles, this entire angle here is alpha. However, we went starting from the terminal side and we subtracted beta to get alpha minus beta that way. But if I start with angle alpha and I subtract away beta on the initial side, so on the other side of my angle here, that means that the angle from B to the origin to D, this angle is also alpha minus beta. So the arc from B to D has the same measure as the arc from A to C. So what that means for us is if I take a look at these two chords, so I have the chord AC and I have the chord BD, those two chords have to be the same. So to summarize that, just based on the way that these angles are laid out, the measure of arc AC, that has to be equal to the measure of arc BD. Just doing a little bit of subtraction. That also means that the segment, the chord AC, that has to be congruent to the chord BD. There's a property in geometry that says chords that intercept arcs of the same measure have the same length. So we can say that they're congruent, and that also means that their lengths are the same. So I could write that with equality as well. All right, so now if I know that these are the same, their lengths are the same, I can figure out their lengths with the distance formula. So let's just jot those down quick. So we have AC, and then with the distance formula, so subtract our x values, x2 minus 1 squared, subtract our y values, y2 minus 0 squared, and the square root of all that. So there's the distance of the length of AC, and then doing the same thing for BD. So let's see our two x values, x3 minus x1, and then our two y values, y3 minus y1. So these two distances, they have to be equal. So I'm going to take these two expressions, my two roots here, that represent the distance of both of those chords. I'm going to set them equal to each other, and I'm going to do a little bit of simplifying, a little bit of rearranging, and hopefully end up with something that we can use to describe the cosine of this angle alpha minus beta. So setting these equal to each other. And I'm writing everything down here. We will get some nice simplifying right away. So y3 minus y1 to finish up. Square root of everything there. Now the first step in simplifying this is they both have a square root. So if we square both sides, that will simplify. And we're just left with the radicand on the inside. And here we have minus 0, so I'm just not going to write that in. And then our second side here. Okay. The next thing, I have lots of multiplying to do. These are all, for the most part, binomial squareds, and we do have a shortcut for that. So the first one here, so we have x2 squared. We'll have a negative x2, and then we'll have a second one of those, so minus 2x2, and plus 1. And then we have y2 squared. All right, the second one here, multiplying that all out, we'll have x3 squared. In the middle, we have x3 times x1, and then doubling that, so minus 2 x1, x3, and then plus x1 squared. And then the last little bit of multiplying, following that same pattern, y sub 3 squared, minus 2, y1, y3, and then plus y1 squared. All right. Now it looks like a lot. We have lots of x's, we have lots of y's, but there is some nice, easy simplifying we can do with some clever substitution. So because we are working with the unit circle, we know that the radius everywhere on here, the radius is 1. And we discussed the property before that for any point that's on the unit circle, just applying the Pythagorean theorem, we know that the x value squared plus the y value squared is equal to the radius squared. So for example, for this coordinate b, and I'll just jot this down here so we can see, for this coordinate, we know that x1 squared plus y1 squared, that's equal to the radius squared, which is just 1. And that works for all of these points. So over here, x2 squared plus y2 squared, that has to be the same as the radius squared. And for this point, x3 squared plus y3 squared, that has to be the radius squared as well. So down in our algebra, anywhere I see an x1 squared plus y1 squared, I can substitute that with 1. Wherever I see x3 squared and y3 squared, I can substitute that with 1. So let's do some rearranging. So we got x2 squared and a y2 squared. So that's good. Let's see, I forgot the plus sign there. So that will turn into 1. And then I'm just going to rewrite the rest of this. On the other side, let's see, we have a x3 squared. Here we have a y3 squared, so I'm going to group those together. We have an x1 squared. Here's a y1 squared. So we'll group those together. And then we're left with this minus 2x1 x3 and minus 2 y1 y3. So these two grouped together, that's equal to 1. These two also equal to 1. And those two are equal to 1. So doing that substitution, gets rid of lots of those x's and y's. So that's equal to 1. We have another 1. And then just copying down the rest. All right, let's do some more simplifying. We have some like terms we can combine. So 1 and 1, so that's 2. 1 and 1 here is also 2. All right, we have a 2 on both sides. So if I subtract 2, we can simplify that. Minus 2x1, x3, minus 2y1, y3. Everything has a common factor of negative 2 in it. So let's divide the entire equation by negative 2. And we are left with x2 is equal to x1, x3, and plus y1, y3. So that looks a little bit better. Got some nice patterns there as well. But it still doesn't tell us what the cosine of our angle is. However, since we are working on the unit circle, we know by the definition of sine and cosine, we know that the cosine is the x value of the coordinate, and we know that sine represents the y value. So just going backwards, if I go and find x2, so x2 is right here. So the cosine of the angle that goes to this point, that's the same as x2. So this angle, that was alpha minus beta. So x2 is the same as the cosine of alpha minus beta. If I do the same thing for my x's and y's on the other side, let's see, so x1, looking up here, here's x1. So this is the x value. So the cosine of this angle represents that x value, and that is beta. So we got the cosine of beta. And then for x3, that's all the way down over here, x3 there, so the cosine of that big angle, which was alpha, gives me x3. And now for our second set there, the y's, same idea, but now we're just using sine. So y1 is right here. The angle that matches up with is beta, so that is the sine of beta. And then y3 is down here, and that goes with alpha, so the sine of alpha. Now I'm just going to switch the order around since multiplication is commutative. We end up with the cosine of alpha minus beta is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. And there is the difference of cosine. Now we can do a very similar argument, follow a very similar process for our other sum and or differences. However, now that we know one of them, we can actually use this to derive the other ones. For example, if I want to figure out the cosine for a sum of two angles, I would replace beta with the opposite of beta, subtracting a negative that turns into plus. And then in here, I would substitute in the opposite of beta, and I can use my properties, my identities, for even and odd functions for sine and cosine. I can do a little simplifying, I can end up with another one that way. So there we go. So hopefully that all made sense. And that is just one of our sum or difference identities.